Hey everyone, it's Mr. Kabbalah. This is unit number 9, section number 2 on testing the mean. What I do in this one is I show you how to do it on Google Sheets, then I show you how to do it on a TI-84, and then we go over what those numbers mean. So there's 4 examples in total. 2 of them use z-test, 2 of them use t-test. It goes over why and when you should use each of those. So if you have any questions, let me know, and enjoy!
All right, so in section 9.2, it begins with a review of 9.1, concluding a statistical test. The big thing is that we compare the p-value to the level of significance alpha. If the p-value is less than or equal to that alpha, we reject the null hypothesis. If the p-value is greater than alpha, we do not reject or we fail to reject the null hypothesis. So less than or equal to reject, greater than do not reject. Okay, so this is the sunspot problem. They gave us a population mean of 41, a population standard deviation of 35, 40 observations, level of significance of 0.05, and we are testing the null hypothesis that the mean is actually 41. So I'm going to do this part on Google Sheets. So sample mean equals average, and I'm going to highlight all of the data over here. All right, so there's our sample mean, 47.04. Sample standard deviation, we don't really need to do this. I'm going to do the .s, but it's good practice. And again, you could also just type in A2 colon A41. You don't have to highlight. So there's our sample standard deviation. This was given to us in the problem. All right, p-value. This is where we're going to do a z-test. We do a z-test here because we know what the population standard deviation is. So we're going to highlight our data first. Again, you could type it in A2 to A41. Then comma. Now the value we're going to test that against is the population mean. So 41, I'm just going to highlight that cell D3. And then the standard deviation, if we know it, which we do, 35, end parentheses, and it gives us our p-value. Excuse me. This is the number right here that we are going to compare to the level of significance, but we'll do that in just a minute. Now, it doesn't ask for this in the problem, but let's say that we wanted a 95% confidence interval. So the confidence level is 95%. I'm going to make it 0.95. So the margin of error, we would calculate that by doing equals confidence. And we're just going to do regular confidence interval. Now this is where it gets confusing because they use this word alpha, and we have been using alpha for level of significance. They're using it as the confidence level. And they also do it, if you want a 90% confidence level, then you would enter 0.1. We want 95%, so we're going to enter 0.05. The standard deviation I'm going to have as the population standard deviation. You could either type in 35 or I put in D4, and then population size, we're going to use a sample size of 40. Again, you could type in that number. I just referenced the cell. So our margin of error is 10.85. Now we use that on Google Sheets to help us create our confidence interval. We need an upper and a lower bound. I'm going to do the upper bound here. That's where we're going to take the sample mean and we are going to add on the error. And then equals, this is going to be the sample mean minus the error. Okay, so we have a lower of 36.2 sunspots and an upper of 57.9 sunspots, and we'll go over what that means in a little bit. Okay, this is how you can use your calculator to do the calculations for the sunspot problem. One thing you'd have to calculate either on a sheet or separately is the sample mean. I got a sample mean of 47. I think 47.04 or something like that. I just made it 47. All right, so let's first get the p-value. So we're going to do stat. We're going to move over to tests, and we're going to do number one z-test. Okay, we're going to keep it on stats if you use data that's using the lists like L1, L2, L3, and so on, and you can surely do that if you want to. All right, in this one, we had a mu of 41, a standard deviation of 35, an x-bar of 47. We had 40 observations, and we were testing to see if it was increasing, so going up greater than the mu. And so this will give us our p-value right here, 0.139. Now, if it's a little different than a Google Sheet, it's a matter of rounding. It should be pretty close, though. 0.139, 0.137, somewhere around there. Okay, now if we want to get the confidence interval, I know it doesn't specifically ask for it in the problem, but throughout the whole section here we do that, so might as well keep it consistent. So again, stat, tests, and this time this goes back to unit number 8. We're going to do choice number 7, a z-interval. Okay, we're going to keep it on stats, 35, yep, 47, yep, and 95%, and it will tell us the 95% confidence interval, 36 point, let's say 2 to 57.8 or so. That's how you do the sunspot problem on the calculator. We'll go over what these numbers mean in just a moment. All right, so now what we're going to do is go through what these numbers mean. I took a screenshot of the Google Sheet. I know, again, you could use a calculator too, but I have the Google Sheet numbers right here. They're all in one spot. So let's go back to the sunspot question. Again, there's a screenshot of everything. So what does this tell us in terms of the hypothesis testing? So let's actually write down our null hypothesis should have been that the average was actually 41. We were going to test to see if they were increasing, so greater than 41. To do this, what we're going to do is take a look at our p-value right here. P-value is 0.1, let's say 4. So since 0.14 is greater than our level of significance 0.05, okay, we fail to reject. We do not reject the null hypothesis. So that means the data are not strong enough to suggest that the mean number of sunspots is increasing. Oh, that's right. This one didn't ask for it, but going to the confidence interval, notice right here, there would be the confidence interval between 36.2 and 57.9. So we can be 95% sure, 95% confident that the true mean is between those two values. And if you think about what we just said, we're not rejecting the null hypothesis that it's 41. And 41 is within that 95% confidence interval. So it kind of jives back and forth that it's not going to be great. It could be greater than 41. I mean, there are numbers in that 95% confidence interval that are, more than 41. It goes all the way up to almost 58. But we can't reject the fact that it might be 41. So I think those two things jive back and forth, which is kind of interesting in a nerdy statistical type of way. All right, so this is the red blood cell volume problem. It gave us the population mean, 28, standard deviation 4.75, 7 tests were completed for, I think, a patient. So let's get the sample mean equals average. And we're going to just highlight, or you could, oops, end parentheses. Okay, there's a sample mean. We don't necessarily have to do the sample standard deviation, but it's good practice. So stdev.s for a sample standard deviation. There it is. It says use a level of significance of 0.01. So to get the p-value, we're going to do a z-test. We're going to do a z-test in this case because it gives us the population standard deviation. We'll see in just a little bit. If we don't know the population standard deviation, we do a t-test. So the data, comma, value, we're going to compare this to the population mean, and then the standard deviation, 4.75. Okay, so this would be our p-value that we're going to compare against the level of significance in just a few minutes. It then goes on to ask us for a 95% confidence interval. So confidence level is 0.95. So we're going to calculate the margin of error using equals confidence. And just like I mentioned before, this alpha is actually referencing the confidence level, actually 1 minus the confidence level as a decimal. So 0.05 if we want 95% confidence level. Standard deviation, we're going to use a population standard deviation. And then the population size would be the sample size in this case, so 7. And it gives us a margin of error 3.5, let's say. All right, and then we use that to create the interval. We would take the sample mean, make sure you're clicking on the right one. Upper bound, we're going to add the margin of error. And then for the lower, we're going to take the sample mean. Again, be careful, you're clicking on the right one, minus the error. Okay, so those are the values I got on Google Sheets. And we'll go on to say what they mean in just a minute. There is something I failed to mention with the red blood cell volume problem. The p-value, the Google Sheet can only give a right tail test, so that number or above. In this particular problem, it said it didn't matter whether we were above or below. We actually had to have a two-tail test, so we actually need to take this p-value and multiply it times 2 for above and below. So our p-value is actually going to be this, the 0.00, let's say 9. Okay, so that is for the red blood cell volume problem. Make sure you double that p-value for a two-tailed test. And here's how you can do the red blood cell volume on the calculator. We're going to hit stat, go over to tests. I'm going to do the z-test first. We do a z-test when we know the population standard deviation. The next couple of examples are going to go over where we don't know the population standard deviation. Would be using the t-test, but for now, z-test. Okay, again, data we could do if we have L1, L2, and L3 like that. I'm just going to type these in. We had a population mean of 28. This was 4.75. The sample mean I got from the Google Sheet, 32.7. You could also just do it right here on your calculator. The sample size was 7. And this one we were just testing, it's not equal to that 28. And it gives you the p-value right here. Now, to kind of compare and contrast the Google Sheet to the calculator, I believe the calculator does two-tailed tests better. It basically just does it, boom, right there. Whereas on a Google Sheet, you have to double the p-value for a two-tailed test. So a little, not too big of a deal, but, one less thing to do, I guess. So let's get our interval. So we're going to go here. We're going to do choice number 7, a z-interval. and 4.75, 32.7, 7.95, and then there's our interval, and we'll go over what those numbers mean in just a moment. All right, so to kind of conclude the blood volume per body weight problem, what we found, I have the screenshot here. So first, what we're going to do is say that, notice that the p-value, and again, we had to double this one because it was a two-tailed test. Let me actually go through this. The null hypothesis would be that it was exactly 28. Now, our alternate, it says that is different from. So we were testing to see it's not equal to 28. So it's a two-tailed test, so we actually had to double the p-value on our Google Sheet. Again, the Google Sheet can only go to the right, so we want to go to the right and then double that for either end of the normal curve. In any case, what we found, the p-value of 0.009, I rounded, is less than or equal to alpha, which was 0.01, which means we reject the null hypothesis. So the data is strong enough to suggest that the mean is not 28 milliliters per kilogram. Now, it went on to ask for a 95% confidence interval. We're going to see if that jives with what we just said. And so again, what we just said is that we're rejecting the null hypothesis. It's not 20. We have good reason to believe it's not 28. So if we go down here, here's our confidence interval, 29.2 to 36.2. Okay, what is it? So we're 95% confident that the true mean is between 29.2 milliliters per kilogram and 36.2 milliliters per kilogram. Now, does this support your decision? Now, we rejected it, and it does support that because we're 95% sure. 95 out of 100 samples that we take are going to have a sample mean that's in between these two numbers, 29 and 36. Now, the null hypothesis saying that it's 28 doesn't fall within that 95% confidence interval, so the fact that we rejected it kind of jives, makes sense with what we're saying here too. So you could write something like that. Does it support? Yes, I guess if you want to just write a one-word answer. All right, so this is the one about the new drug to treat leukemia. It gave us the population mean, the sample size, it gave us a level of significance of 0.01, and eventually it's going to ask us for a 95% confidence level. What it doesn't give us is the population standard deviation. So this is, we don't know this right here, so I'm going to gray it out just so we know that we're not going to fill that part in. All right, so let's get the sample mean. That's average of, and we're going to get for the new drug. Oops, there's only from there to there. All right, and that's weeks in remission. Sample standard deviation, stdev.s of these. That was given to us. Now for p-value, because we don't know the population standard deviation, instead of a z-test, we're going to do a t-test. Now, before we do that, the way Google Sheets is set up, it wants to have a value paired with every piece of data in this data set here. So if we want to compare it to this 12.5, I'm going to drag this down to have a 12.5 in every box so that each data set or each data piece of data has a pair with it. Because in our equation, excuse me, when we do a t-test, it wants two ranges. So range 1 would be those, and I'm going to have to fix this. Sorry, give me a sec here. I forgot a 12.5. There. All right, so equals t-test. Range 1, comma, and then you got to have your range 2, and it has to be the same number of numbers. That's why I'm doing that. Tails. Now this is where this one you can actually tell it one-tail or two-tailed. We just want a one-tailed test to the right. It defaults to the right. And type, this gets a little confusing. We're going to just set it at 1 for now. I don't think we'll get to the others. And then that gives us our p-value, and that's what we compare to the level of significance, which we'll do in just a moment. The margin of error, this is where we use confidence. Excuse me, sorry. But in this case, we're going to do a t confidence level. Again, this alpha is confusing because we've been using alpha as the level of significance. Their alpha is the confidence level. In any case, the standard deviation is going to be the sample standard deviation. So good thing we calculated that. And then the sample size, 21. So there's our margin of error. So we can now calculate the interval. So we're going to take the sample mean, and for upper, we're going to add on the margin of error. And then for the lower, we're going to take the mean and subtract the error. Make sure you're clicking on the right things. If you click the wrong box, you're going to get some funky values. All right, so we'll go over what these values mean in just a moment. All right, for the weeks in remission of the new drug versus the old drug, let's do our, now because we don't know this, the population standard deviation, when we do our test, we're going to do a t-test, student's t-test, when we don't know the population standard deviation, which is in most cases actually. So again, data would be if we have it in our lists. The mu it gave us as 12.5. The sample mean I got at 17.1. The sample standard deviation I had it was like 9.999, might as well make it 10. Sample size was 21, and we were testing to see if it was greater than 12.5 weeks. So we're going to change it to greater than and then calculate. So again, it gives us our t-score, our p-value, which is the main thing we're going to look at, and then the rest of it. If we wanted to do a confidence interval, which it does ask us to do, we'd hit stat again, over to tests, and make sure you go to t-interval this time. Just like I said, we use t when we don't know the population standard deviation. T-interval, fill in what we have, 17.1, check, 10, 21.95, calculate. Okay, and there's our interval. Again, it might be slightly different than what we got on the Google Sheet, but it's a matter of rounding and slight changes here and there, but it should be pretty darn close. All right, so this is a new drug treating leukemia problem. We don't know the population standard deviation. So let's go through what these things mean. But actually, I guess first let's get our null hypothesis was that the mu was equal to 12.5. And we wanted to see, is it longer than that? So is the remission time longer than the 12.5? So greater than 12.5. We got a p-value of, right here, 0.024, which we're going to compare against the alpha, 0.01. 0.024 is greater than 0.01. So what we do is we fail to reject the null hypothesis. So in other words, the data are not strong enough to reject mu being 12.5. Okay, if we wanted to construct a 95% confidence interval, then we would actually use this down here. So 12.5 to 21.6. What does this mean? We are 95% confident or sure that the mean is between 12.5 and 21.6 milliliters per kilogram. And does this support our failing to reject the null hypothesis? Well, our null hypothesis says that it was equal to 12.5, and 12.5 is the lower end of this interval, but that's part of the interval. So it kind of does jive with that, or it agrees with our not getting rid of 12.5 as a possible mean. We're 95% sure of that. All right, so this is the arrowhead problem and the archaeologist. I don't know what, there we go. Go away, go away. All right, so we have 61 pieces of data at the new site. The average at an old site was 2.6. We're going to let's do the sample mean first. So equals average of all of this. So I'm going to highlight this time, and maybe for the next few times, just type in the numbers. All right, so there's the sample mean. Notice that the sample standard deviation I shaded out, it's not given to us, so we're going to calculate the sample standard deviation, stdev.s. I guess I lied, I'm going to highlight. Wasn't too bad. Sample standard deviation, level of significance 0.01. All right, the p-value we're going to get by doing a t-test. Now we're doing a t-test because the population standard deviation was not given to us. A t-test. Oh, actually, before I do that, with Google Sheets, it wants a paired number comparing these two. So I'm going to take the average mentioned 2.6 and drag it all the way down so that every number on the left has a corresponding 2.6 on the right. So that way I can just do a t-test between two ranges. So we're going to do a t-test from this one, comma, and then I'm going to go this one, but back up to the top. All right, and then it wants what type of tail. So this was asking, are they longer, greater than 2.6? So this is going to be perfect because we can just do a one-tailed t-test. It automatically goes to the right on Google Sheets. The type we won't get into too much, just do a 1, and then there's our p-value. Now, if this happened to be a two-tailed test, like not equal to, we would have to double that. But this is just to the right. So that's our p-value that will compare to the level of significance in just a moment. It does ask us eventually to construct a 90% confidence interval. So margin of error, confidence, and again, because we don't know the population standard deviation, we're going to do .t for student's t-interval. This one we're going to do a 0.1 because it asks us for a 90% confidence level. Oops, I didn't finish. All right, the standard deviation will be the sample standard deviation. And then the sample size was 61. And then that should give us our margin of error. And so that means that our interval will be the sample mean, and be sure you're clicking on the right things, plus the interval for the upper bound, and then for the lower bound, sample mean minus the error. That's what I got on Google Sheets. The last problem about arrowheads, we're going to do stat tests. T-test, because we don't know the sample, I'm sorry, we don't know the population standard deviation. Maybe that'll be the last time I say that. 2.6, I got a sample mean of 2.92. So I got a sample standard deviation of 0.85. This was 61. And we were still going for greater than the average, seeing if they increased. Calculate. And again, we got our t-score, our p-value, and that's what we're going to use for now to compare against the alpha, or the level of significance. To do the 90, now this one was a 90% confidence interval, so t interval for this one. We got 2.92, 0.85, 61, and this time 0.90. And it's going to come up with our confidence interval. For the arrowhead problem, our null hypothesis was that the average is 2.6 centimeters. We wanted to test, I believe it does say are longer than the arrowhead, so we're testing to see is it greater than 2.6. We got a p-value right here of 0.0022. And again, we would double that if this were a two-tailed test. This was just a one-tailed test. Google Sheets goes to the right. So if you want to go right and left, you have to double it, which I believe one of the examples before we did have to double it. This one we don't. 0 to 2, let's say, and that is, oh, I'm sorry, I forgot a 0. It's 0, 0 to 2, which is less than or equal to our alpha, which is 0.01, which is 1% as a decimal. So when our p-value is less than or equal to the alpha, the level of significance, then we reject the null hypothesis, which means that the data are strong enough to suggest that the mean, and this is where we kind of adopt our alternate hypothesis, so suggest that the mean is greater than 2.6 centimeters. And then if we wanted to go on, and I believe it does ask us for a 90% confidence interval. Did that not? Oh, here we go. I thought it moved on. It didn't. Waiting. All right, so we have our 90% confidence interval right down here. It is from 2.7 to 3.1. So what does that mean? We're 90% confident that the mean arrowhead length, I'll just write the mean, is between 2.7 and 3.1 centimeters. Now, does this support our rejection of the null hypothesis? Yes. Both, and I'm going to abbreviate here, lower bound and upper bound are more than 2.6, which means that the mean of 2.6 is probably not true, that it's probably in 2.7 to 3.1 somewhere, which means that it's more than 2.6. So it does agree with what we are doing with our null and alternate hypotheses.